So today is Wednesday, the 13th. Today we're covering section 9.3, which is convergence of series. We're going to start with something called the integral test. I will say that today is the first in a stretch of many classes in a row where we are going to be introducing different ways to tell whether a series converges or diverges. Remember, for a series, which is where you're adding up a bunch of things forever, to converge means in the forever, in the limit, you are honing in on a single number. And if you don't hone in on a single number, we say that the series diverges. Oftentimes that means you go to infinity, but not necessarily. Last class, we talked about geometric series and we had a fancy formula, a over 1 minus x. Yep. And if we could apply that formula, then we would know that the series not only converged, but we would know what it converged to, what number we would get in the limit. Geometric series are almost unique in that very few series can we actually tell what the thing adds up to. Most of the time, we're going to just have to content ourselves with saying it converges or it diverges without knowing what it converges to, should it converge, okay? So geometric series kind of an outlier in that regard. All right, let's get started again on page 19. Our summary. In this class, we begin our study of convergence tests. So these are theorems that will help us decide whether or not an infinite series converges. Let's begin here with our demo. Just one quick reminder, the test corrections are due Friday, start of class on Friday, okay? All right, recall a series converges if the sum of all the terms is finite. We're going to quickly analyze the series below. We've got 4 of them to do. Let's give it a shot. We'll start off by writing the first 3 terms of each of these guys. So for part A, beginning by plugging n equals 1 in, what do we get? Over 14, super. And then the sigma means plus, and now we plug n equals 2 in. $29 is good. Let's do one more. I didn't do that one myself. All right, negative 25 is good. 54. You could split them with commas if you wanted to list the terms. I'm just highlighting the fact that the series means add them. Yeah, but you're right. The directions up above, which we didn't read, say list the terms. I did not do that. I'm adding them up. Okay, and then it goes forever. And I don't know. I don't see any pattern in here. I don't know what's going on with that series. Let's just list the first 3 terms of some of these other ones, which hopefully will be easier than that one up there. This guy right here, 1 over n, we talked about a little bit last class. 1 plus, now n is 2 is half, plus third, n just goes up by 1 every time. The next series, 1 over n squared, 1 plus quarter, that's the 2 squared, and then skipped 1. Not quite. Right. Yep. Okay, quarter plus a 9th plus forever. All right, and then this last guy. So we'll start with n equals 1 on this one. What do we get? Just a 7 times the 1, right? Plus, okay, now n is 2. 14 thirds, right? 7 times 2 thirds. Plus, now n is 3. 28 ninths is good. Plus, dot, dot. Okay, we've got 4 series here. We're going to decide for 2 of them whether they converge. For the other 2, we don't have the tools yet, but we will in just a minute. Okay, this last series right here has a very special name. What kind of a series is that? It is a geometric series because you keep multiplying by the same magic number, which is what in this case? Is 2/3. Might not have realized it as we were just doing the calculations, but that 2/3 to the n minus 1 is a giveaway. Every time you increase n by 1, you're just getting another 2/3. So you just keep multiplying by 2/3. So this guy right here is a geometric series with, and I think we called it x was our name for the magic ratio, the multiplier. What's our range of x's that make it converge? -1 to 1. And our particular x lives in that range. So since 2/3 is less than 1 and greater than -1, this geometric series does what? Super. Okay, so that's part D. Let's jump back up to part A, the one with the crazy sets of numbers in them. I want to think about what these terms are approaching when n gets bigger and bigger and bigger. There's a lot of stuff we can ignore in that fraction, right? If n is huge, then the 2 on the top is pretty much irrelevant, and the +9 on the bottom is also irrelevant. So what do these terms approach at the end of the day? Limit n goes to infinity of that whole fraction. Right, because we can ignore the 2 and the 9, and then we've just got -3n squared over 5n squared, and you cancel those n squareds, and the limit is -3/5, right? So that series essentially becomes add -3/5 over and over and over again forever, right? The terms won't ever actually exactly be -3/5, but they'll be really close. So if you add -3/5 forever, what are you going to get? Negative infinity, right? So does this series converge or diverge? Yeah. So the series diverges since the terms don't approach. There's only one magic number that's going to give us any chance of having a finite sum when we do this forever. It's 0, right? We were adding -3/5 forever, you're going to get minus infinity. If you add 0.1 forever, you're going to get positive infinity. In fact, you add any number forever, you're going to get infinity or minus infinity unless that number happens to be 0, all right? It is not geometric. No, there's no multiplier that you can keep using that will get you from one term to the next. Okay, what about in part B? What did the terms go to? 1, 1/2, 1/3, 1 over n. What are they approaching? They're going to 0. How about the 1 over n squareds? Also going to 0. You cannot conclude anything by getting 0. If you don't get 0, right away you make the conclusion. But it turns out one of these 2 guys, they both have the same end behavior. They both go to 0. One of them converges and the other one diverges. So it's really risky to read too much into the fact that the limit is 0 for any of the terms. So both unknown at this point. We're going to fill in the blanks on the next page. Number 2 is our first brand new test today. The series above, that first one that has no chance of converging, fails what we call the nth term test for divergence. If the limit of the terms is not 0, then right away we know the series diverges. That's it. We got -3/5. It wasn't 0. The series diverges. That test has a name. They're all going to have names over the next few classes. Questions on that one? Okay, let us take a look at part B, the sum of 1 over n, 1 plus 1/2 plus 1/3 plus ... It's got a musical name. It is called the Harmonic Series, and whenever we want to reference it, which will be pretty often, we're going to call it the Harmonic Series. There is only one Harmonic Series. It's that guy. The series is so named because the overtones of a vibrating string have wavelengths half, a third, a quarter of the fundamental wavelength of the string. I really don't know much about music. I like 80s pop, but I can't really relate that to math. Some of you who are musically inclined might understand the sentence more than I do, but in any event, it's got a musical name for some musical reason. All right, number 4. Despite the fact that the terms of the harmonic series approach 0, it turns out that the harmonic series diverges. If you add those terms forever and ever and ever, you will get bigger than any number you can name. It goes to infinity. So we're going to prove this using something called the integral test, and we're going to make sure that we write complete sentences. Some of you will rebel against writing sentences in a math class, which is a very natural response, but you need to get over that response. Call on your inner mathematician, let him or her out, and we're going to write mathematically precise sentences that are incomprehensible to most people. It's all right. So here we go. Here's the graph of f of x equals 1 over x. Remember, we're thinking about the series 1 over n. The only difference is it's become an x instead of an n. We're going to draw some left rectangles on this picture as if I were going to approximate the area underneath the curve between 1 and infinity. Okay, left rectangles between 1 and 2. Which point are we picking? 1. So we go up there and we draw that rectangle, yeah? And then left rectangle between 2 and 3. Which point? 2. And let's do one more between 3 and 4 using the 3. Okay, let's talk about the area of each of these rectangles. Area is length times width. The lengths for all of these are 1. Well, let's talk about the height, I guess. What's the height for the first one? It's a 1, so the area of that first rectangle is 1. What's the height for the second one? It's a half because we used x equals 2, and plugging x equals 2 in gives you the y value. So that area is a half times 1. The next one, the height is a third. So the area there is a third. And so if you do this forever, the sum of the areas of the red rectangles is the harmonic series. 1 plus a half plus a third plus forever. Yes? But what do you know about this integral right here? It diverges. We proved a while back that that guy diverged, meaning the area under it is infinite. But the area of the red rectangles is a little bit what compared to the area under the curve? It's a little bit bigger, a little bit greater. Yeah? And the area under the curve is infinity. We've proven it. So the area of all those red rectangles must be infinity as well. Great question. 6.
So, well, just so for 5, we know that diverges because we know that the integral of 1 over x.
Yes. We're going to write those complete sentences that I promised. Let's talk about 6 first, and then we'll fill in the sentences for 5 and 6. Okay, 1 over n squared, we're going to graph 1 over x squared, which looks an awful lot like 1 over x, but you will notice that even though both of these curves approach the x-axis as you go to the right, there is a difference. This guy approaches the x-axis a lot faster, doesn't it? Look at the two curves on your page. Right, they're both heading to the x-axis, but this one goes a lot faster. So let's see what happens here. This case, we're going to talk about the area under the curve, the 1 over x squared curve. But instead of left rectangles, we're going to choose right rectangles. You'll see why. So between 1 and 2, which point are we picking for right rectangles? We're going to pick the 2. So there's my first right rectangle. And then between 2 and 3, which one do we pick? We pick 3. There's my second right rectangle. I'm going to have a hard time drawing the one between 3 and 4. These rectangles are really, really tiny, right? That doesn't mean that the thing is going to converge. We're still adding infinitely many positive numbers. But these rectangles are a lot smaller than the ones that we drew up above. Costanza? You'll see in just a second. Yeah. Okay, let's talk about the areas of these rectangles. Again, the width or the base of each rectangle is 1. What's the height of this first rectangle? It's a fourth, right? Because it came from x equals 2 plugged into the formula gives a quarter. So the area of that rectangle right there is a quarter. The area of the next rectangle is determined by the 3. The y value is 9th. So the area of that rectangle is a 9th times 1. And the next one is a 16th. Now you'll remember that the first few terms of this guy, what was the first guy, first term? Was 1, and then plus n equals 2 is a quarter and a 9th and a 16th. Now the fact is we don't have the 1, but outside of that we've got everything, right? Okay, so ignoring the 1, let's just think about the integral right here. Does that guy converge or diverge? That one converged. We proved this a while ago, but if that power was anything greater than 1, the integral converged. And so this power of 2 says, yes, that integral converges, which means the area under the blue curve, all of this area in here is what? It does converge, so the area is what kind of a thing? Finite. So how about the sum of the areas of all of our red rectangles? It's also finite because it's smaller. Costanza, this is why we picked underestimates here, because we knew ahead of time that we wanted to be less than something finite. So that's why we picked the underestimates. So ignoring the plus 1, if you add up all of these things right here, it is definitely something finite. Okay, so let's bring in the plus 1 that we missed out. Add 1 to our finite number, and it is still finite. So that sum, 1 over n squared, converges. Yeah? The total area? Great question. Number 7. So you guys just write the packet. I don't need to be here. Okay, so although we're able to use the integral test to see that a series converges, and we'll get back to our sentences, but you guys are pulling us down. So typically we have no way of knowing what a series converges to. All we're going to say is, hey, it converges because we have this test. But in this particular case, there's a genius mathematician from back in the 18th century named Leonard Euler, and he discovered that the sum of 1 over n squared, so Igor said, does it approach 1? So reasonable guess. Turns out it approaches pi squared over 6. A much less reasonable guess, but turns out to be the right guess. So we're going to take a quick look at an Excel spreadsheet. But supposing that by some miracle this is true, that if you add these guys up forever, you get pi squared over 6. I want to solve this equation for pi. So multiply by 6, and then take the square root. So if this equation is true, then the square root of 6 times that summation is going to equal pi. Yes? Just solving for pi. Okay, so I made an Excel spreadsheet. It did not take long. Here it is. The first column is just n's, counting starting at 1. The next column is n squared. I'm going to focus on this row right here. So if n is 2, n squared is 4. Then I do 1 over n squared. So we're doing 1 over 4. Excel is going to do everything as decimals. So 1 over 4 is this 0.25. Then we're going to do the partial sums. The first 1 over n squared was 1. And then we add 0.25 and we get 1.25. So that's just 1 plus a quarter, right? And then we add a 9th, which is this number. And we add a 9th to 1.25 and we get that number. Fair? And then the last thing I did, it's going to be hard in the back to see this thing. I can't make it any bigger. But it just says equals square root of 6 times this column, which is exactly what we did when we solved for pi in that other equation. So if Euler was right, what should happen to these numbers here as we go down this list should approach pi. All right, so we start at 2.7. That's not very great, but all of a sudden we're at 3.13. And okay, so we're at 3.14. It took about 600 terms to get to 3.14. Now, if that's all you've memorized, you might be excited right there, but some of you know more digits of pi. What's the next one? Yeah, okay, so then the scroll wheel doesn't doesn't cut it anymore. So we gotta pull down a little bit faster. Okay, 3.141. What's after that? It's a 5. Right now we're at 3.1413 instead of 15. So we can keep pulling. Anybody know the next digit after the 5? The 9. All right, so we keep going. And you can see now. Right now we're 40,000 terms in, and we're slowly watching this digit here. Hopefully approach a 9, and so we just keep going, keep going, keep going. Yeah. So it well, we're getting there. So that's 100,000 terms, and we're getting there. Yeah. Right. So so there you go. So typically, you know, like we don't know what the thing adds up to. All we're going to say is it converges. But if you happen to be a particular genius like this guy, you might have some insight. Okay, so let us go back up and start writing in some of these sentences here. Going back to the first guy, that harmonic series, the 1 over n, there were some characteristics of that graph that we need to take advantage of. So first of all, the fact that every one of these rectangles was an overestimate was a characteristic of that graph. What was special about that graph that made all these rectangles be overestimates? Was it the concavity? Or was it the decreasing? The fact that it's decreasing made these rectangles consistently be overestimates. How about in the next picture? These were all underestimates, but what was the feature of the graph? It was decreasing. So what we need in order to do this kind of argument is a graph that is consistently decreasing. Because if you have a graph that's going up and down, then some rectangles will be over and some will be under, and you won't be able to take advantage of the nice logical, hey, the area under the curve is finite, and all of these rectangles are smaller. So the rectangles must be finite.
If it was an increasing function, would that mean that underestimates would be overestimates?
Yes. Yeah. Okay, so we needed everybody to be, we needed to be decreasing. And the other thing we're going to take advantage of, we're not going to talk about too much here, so we need the function to be decreasing. We also want the function to be positive the whole time. You can think about like why we would want that to be true. But in any event, here's the formal write-up of this thing that we're going to call the integral test. So f is just the function, like 1 over n squared. We need it to be decreasing and positive. And then if you do the integral of that f function, if that integral converges, then so does the series. And if the integral diverges, then so does the series. And we're not going to get caught up in the details of are we using left rectangles or right rectangles. The fact is, one of the rectangles will give you the conclusion you want. So don't even sweat which one you need. Just know that the integral and the series behave the same way, right? So let's officially write it up here in number 5. Okay, we're just going to give a name. A sub n equals 1 over n. Just give a name to the terms. Maybe I'll put the word let in here. Let a sub n equal 1 over n. Then that list of numbers, the a sub n's, are clearly decreasing, right? 1 over n's are getting smaller and smaller, half, a third, a quarter, a fourth. And they are all positive, right? We're never going to get down to some negative number with this 1 over n. And so with those two hypotheses written out, the integral test is in play. We get to use the integral test. We know that the integral of 1 over x from 1 to infinity converges or diverges? Diverges. I'm going to write here, this is an earlier result. Something we proved earlier this semester. I don't know that we had a name for it. Did we? Was this the useful? Well, maybe this was the UIC. It was. Hey, let's name it. UIC. I don't remember the letter. What was the letter for the? It was P. b equal to 1, which was less than or equal to 1. Super. So we got lucky here that we had a previous result we could rely on. But in the activity, you're going to have some integrals that you just haven't seen before, and you can't rely on a previous result, and you're going to have to do like this whole separate problem. Does the integral that you're looking at converge or diverge? And you'll do the whole, change the infinity to a b and do an antiderivative. Like you have more calculations to do usually than this. Okay, we know that that integral diverges. Therefore, by the integral test, our series, and we're just going to actually copy it, 1 over n equals 1 to infinity, also does what? Diverges. UIC was our useful integrals for comparison. Yeah. So it's, yeah, Sam.
So you decide whether or not to use left or right hand something. You can use either because why? So you're allowed to use either.
Mm-hmm. Mm-hmm. So we choose the one that works, and then we decide that because we can always make a good choice, we're not going to make any choice at all. You could have chosen to use left rectangles for this picture. Right rectangles for this picture. So that would be your first one. That would be your second one. That would be your third one. You would end up with basically the same series, a half, a third, a quarter. We wouldn't have the 1, but that's not a big deal. And the area under the blue, that's this integral. We know it's infinite, but that tells us nothing about the area of all these purple rectangles.
Yeah.
So the purple is not a good choice.
But you're allowed to do that
because we're not saying the areas will be the series. We're saying that the integral and the series behave the same. You said consistent, it's kind of like the integral.
Yeah.
So if the integral diverges, then so does the series. And if the integral converges, then so does the series. Depending on which of those two cases we're in, you're going to choose either left or right rectangles. But we're not going to worry about which one we have to choose because we've seen in these two examples, 5 and 6, we saw that, hey, if you need to use left rectangles to make it work, then you'll get the conclusion. That's what we saw here in 5. In 6, it turned out right rectangles gave us the conclusion. But they're both just encapsulated in this thing called the integral test. So we don't need to worry about like which one we should be using. Yeah. Okay. Yeah, and it's going to work one way or the other. Yeah, so we'll just say that it's going to work. There's a lot of stuff going on in the writing here. It's fairly dense, but I'm hoping that the process will become clear as you do a few more examples. You got to make sure that you convince me that the series is decreasing and is greater than 0. Sometimes even the decreasing part, like that's not always obvious. 1 over n, yeah, sure, it's always decreasing, but you might see some in today's activity where it's not clear to you that this brand new thing is decreasing. Showing something is decreasing is a Calc 1 thing. How do you show something is decreasing? Derivative, and hopefully see the derivative is what kind of a number? Is negative, right? If the derivative is negative, then the function is decreasing. So you might need to do that today for some that are less familiar to you than 1 over n. So got to be decreasing, got to be positive. You have to tell me something about the integral, and then you need to reference the integral test to get the same conclusion for the series. That's what all the write-ups look like. Okay, so I think that's good. We're not going to write number 6. It looks almost identical to number 5. Yeah, just change the word diverge to converge. No, they're decreasing every time. Yeah, got to be decreasing no matter what. Yeah. Okay, so the activity is on the next page. I am going to point out 2 things. Number 1, it says that you have 3 available tests at this moment. Some of the things in this activity will be geometric series. Some of them will fail the nth term test for divergence. That's what we saw today. Some of them will be the integral test. They're not all integral tests. You have 3 tools. You're going to use all 3 tools in this activity here. The other thing I want to say is that there's an important result embedded inside of this activity, and I want to make sure we all get to it today during class. So you're going to go slightly out of order. Page 21 is where you're starting, then you're jumping to 23, and then coming back to 22. Okay, I'll walk around.